Looks like I am the main culprit for your breakfast. Sorry for that, guys. Okay, I have started recording. Okay.
Yes, sir.
So shall we start the class? Because
Yes.
91 is the class attendance.
Yes, sir. We can start.
Okay.
Yes, sir.
Yes, sir.
Thank you. So I will share the screen and see where I have shared.
Morning, sir.
Yes, sir.
Good morning, sir.
Yeah. Good morning. Good morning. You can see the screen, right? My PPT.
Yes, sir.
Yes, sir.
Very good. Okay. Okay. Good. So yesterday class we had a take-home message that it is very important to understand the stereochemistry of the molecule. Okay, and we are clear with that. So what we are going to try to understand today class, we start from chirality. Okay, I have discussed about the chirality. I have showed how chirality be used in nature. Then we came to the chemistry. Okay, fine. Up to this, I think there would not be any big question. Okay, so we'll start from here, from this slide. Okay, so this is the origin of definition, and you should understand how this definition later on got modified, and finally what is the definition currently we are using. Okay, so this is the first definition started. The first definition stated that a carbon with 4 different groups. So that carbon should be basically a tetravalent carbon, that is sp3 hybridized, and if it is attached to 4 different groups, then we know that the carbon can exhibit chirality, and that particular carbon we can call them as a chiral carbon or an asymmetric or a stereogenic center. Okay, this was the initial definition. So if you see a carbon, a molecule which contains a carbon atom, and if it has a 4 different substituent, we can call that carbon as a chiral carbon. That was the initial definition. It was a very, very nice definition. Okay. Now, before getting to the modification of the, okay, now we'll see how later on this got redefined. Okay. So people started then looking into chirality. After the word chirality came into chemistry, people started looking into chirality. This is an empty slide. I'm going to write something. Okay. So the people, you can see these writings now?
Yes, sir.
No
Yes.
problem, right?
Yes, sir.
Okay, good. So this was an interesting molecule. Okay, they have this ammonia molecule, but the story didn't start from this. I will let you know the story. So this molecule is chiral according to the earlier
No.
definition. The earlier
No,
definition
sir.
says what?
No, sir.
So different groups should be attached.
Yeah,
In fact,
the earlier, yes, very good. The earlier definition says that it should have 4 different substituents. Okay, very nice. So according to that, it is not chiral. So then can I make this chiral based on the first definition? That means I have to have 4 different things. So I am keeping hydrogen. I'm having a deuterium here. I'm having a tritium here. Now according to the first definition, is this molecule chiral?
So according to the first definition, it is.
It is chiral, right?
Yes, sir.
yes.
Yes, this is how we should learn how science get advances. Okay, so this is chiral according to the
Sir.
first definition. Yes, yes.
Yes, sir. Just excuse me once, sir.
Yeah.
Hydrogen, deuterium, and tritium, they both have the chemical properties same. So,
No, they are
chirality,
different atomic
yeah,
atoms.
they are isotopic. So, okay. So it
Yeah,
depends on the atoms.
yeah, yeah.
Oh, okay, sir.
Okay. Yeah. So we can call this as a chirality, chiral molecule, but people did lot of experiment to see the other enantiomer. Okay. See, for example, what should be the other enantiomer of this? If you look carefully, it should be the other way around. Okay. According theoretically, this should be right, like this, right?
Yes.
Yes, sir.
Then the molecule should be chiral, and we can get two different forms. And people did lot of experiments on this, and they found they were not able to see these two different enantiomers. Okay, now well, so they left like that. Okay, then the chirality, they said okay, they didn't work more on this compound, and later on the research stopped there itself on nitrogen chirality. Then what happened suddenly, one of the research group, see, you have to learn the story, then you will understand how beauty chemistry works. One of the research group, they were starting working on this particular atom, and they were thinking that based on this research, this should not be chiral, right? Yes or no?
Yes, sir. Yes.
Yes.
Yeah, but they were successful in getting this compound isolated. So they found two different properties of these two different molecules. This molecule exhibited different property and this molecule exhibited different properties. And they were amazed to see a chirality starting there. Okay. Now you see the reason. So this molecule, which according to my first definition, having four different atoms or four different groups, ends in not chirality, but this, according to the first definition, has four different groups, but ends with the chirality. So now we have to justify this, right? So what is the justification people gave?
So that the energy of amine inversion in the second case is too high, so
Yes.
they can be separated in the
Okay.
separate
Okay.
enantiomers. Whereas in the first case, the bulky groups are not there, so
Very good.
the amine
Yes.
inversion energy
Very
is
good.
not
Very
high,
good.
so the barrier is less.
Very good. So you guys have read it. Very nice. So you see, we call this an amine inversion. We can use this word. It's an inversion. Okay. And this amine inversion, if you look into the energy required, it is 2 kilocalories per mole. It's a very, very, very less number. Okay. And then they went to this compound and they saw the energy. See, this is the beauty of understanding the energy, the numbers. Okay. 24 kilocalories per mole. Anyhow, I'm not going to ask this in exam. What is the numbers? But you should know these numbers to enjoy the process. This is 2 kilocalories per mole and this is 24 kilocalories per mole. Okay. That means the ring flipping or the amine inversion, whatever the term, happens very fast here, so that I am not able to separate these two enantiomers. In this case, it is happening slow. That's why I was able to separate the enantiomer. Okay. So now, according to the science advancement right now, I can call this molecule as a chiral molecule and this molecule as a achiral molecule right now. Okay. Might be in 10 years, you might end up with a separation technique which can separate these two. Then your whole definition will start changing. Okay. So for the current thing, we call this as a chirality. But this molecule also exhibit chirality, but the energy is so low that their amine inversion is fast. We don't have that much fast techniques right now to find it out. Okay. But here the energy is this. That's why we are able to separate this. Okay. That's why we say currently right there this molecule as a chiral. Okay. This is the first thing. So can you redefine the definition right now? How you can redefine the definition?
Sir, if a molecule can be separated into two different enantiomers, then we can see it as chiral.
Okay, that is, can we make it more better? Can you redefine? That is good.
Sir, on the basis of inversion energy, we can define that.
Okay. Can I say that first, the chirality definition, Strong's holds good. One, you should have four different groups attached
Substituents.
to a atom. Okay, it can be carbon, it can be nitrogen, or it can be anything. If you can have a four different substituent or four different groups attached to an atom, you can see chirality first. Okay. The second condition is that, what is the second condition? The second condition is
The
that
energy
the
of
inversion energy should be greater than, so that I can flip on. Now I have given a filling the blanks there. Greater than. What is that?
15
That
kilocalories
is,
per mole.
15
yeah, greater than?
15
15 kilocalories.
Yes, greater than 10 to 15 kilocalories per mole. Now that's how the definition comes in. Okay, see how I am building up the chirality definition. Okay, now for that, to understand that energy, we will do one more example. Then you will understand the energy. Okay, for example, yes sir, anyone? Yes sir. Hello? Hello? Can you guys hear me?
Yes, sir. It's audible.
Yes, sir.
Yes,
Someone asked question, that's why I was okay, fine. Now I'm taking the whole principle again. Now I am going to define the energy, what energy I'm talking about. Okay. So for example, I said that this molecule has hydrogen, deuterium, and tritium. This also can be chiral, but right now it's not chiral because it has only 2 kilocalories per mole. Okay. Methyl. So I will take this border. Okay. This I know that this is methyl. The previous example, chlorine, hydrogen. I said for this it needs 24 kilocalories per mole. See, that's how research goes. Okay. Now I am thinking of taking an in-between molecule. For example, I take an hydrogen here, hydrogen here. Is this molecule is chiral? This second molecule?
No, sir.
No. Why? No. Why?
So because two atoms are same.
Very good.
Hydrogen by
Very good. So always you go with the first definition. The first definition says that there is no four different atoms. Okay, very good. With that, I'm going. So what I'm going to say? Okay, I'm trying to make this molecule chiral by doing some. I'm replacing this hydrogen by this. Is this molecule chiral?
no, sir.
No. Why? Based on the first definition, this is chiral?
Yes, sir.
Yes,
sir. Based on first definition.
Yeah, but later on, what happened?
So
Now,
the
first you are not saying it's not chiral.
energy of inversion may be less than
Yeah,
15 kilograms.
energy of inversion for this particularly ends up around like 22 kilocalories per mole. The hydrogen atom. That means it is replaced by carbon, fluorine, chlorine, bromine, anything, two hydrogens. Okay, then you end up in seeing chirality with the current definition. Okay, that is about 15 kilocalories per mole. That's how you can define currently. Any problem, sir? Sir, if it is clear only, I will go to the step. Otherwise, I won't go at all.
Yes, sir. Clear.
It should be greater than 15 or 10 to 15.
Sir, once
Yeah,
again,
10 to 15. See, it's very hard to find out that particular energy. Okay, so that's why I defined it. I little bit. It's not a book definition. this definition we understand. He says that if the two hydrogen atoms are replaced, two hydrogen atoms, okay, not one. The two hydrogen atoms are replaced other than this hydrogen and isotopes of hydrogen, you might end up in getting chirality. You will definitely get, for example, in the exam, you have like 5 molecules, 6 molecules. We will ask, find out the chiral molecules. Okay? That question will be definitely there. Or we might give you a single molecule with all the atoms and we will ask you how many chirality this molecule can exhibit.
Excuse me, sir.
So, will we be given the values of energy of
No, no, no.
inversion, or
No values will
they
be
will be
given.
very evident?
No values will be given because these are all, you cannot uh, take any molecule and find out the energies. It's very tough. These are certain molecules which we know the energy. Okay, it doesn't mean that for all molecules I make it in the things. But I make a general rule. You go with this. Okay. The thing I say that if you have a nitrogen where two of your hydrogen atoms are replaced by a carbon, chlorine, fluorine, or bromine, then you can have a chirality. Okay, I am telling you, it will work most of the time. Don't worry.
Okay.
Sir, that molecule is not chiral.
Huh?
That's 12 kilocalorie per mole.
This molecule is not. This molecule is not. It's not chiral. That's why I made you a definition. Hydrogen B, hydrogen ka isotope should not be there. The two should be replaced. Two of that. In this case, you see there is one hydrogen
Sir,
already.
if we replace two hydrogen with carbon, let's say one is methyl and one is ethyl,
Yeah.
then it will be chiral?
Definitely. Sir, if you any doubt further, because this is an important point, that's why I'm just making it, ensuring that you know it. I don't want you to go and study again in any book. You won't get it. So that's what I keep on repeating. It might be boring for some best students, but still I want to make sure the class, so that I don't want anyone to get a wrong answer. So if you see a nitrogen chirality, ensure that there are 4 different groups and ensure that they are not 2 hydrogens or not isotopes of hydrogens. It should not be there. Okay? One chalega. One hydrogen you have, because the third example you can see there, it has only one hydrogen, that's fine. You see this is chiral and this is achiral. Okay? Not achiral, they are not isolated. Okay, fine. Any doubt?
There is in nitrogen, there should not be two or more than two hydrogen or isotope of hydrogen.
Yeah, that's clear. It's very clear. Good. Now we are defining it nicely.
So,
Yes,
so
sir.
deuterium and hydrogen do not act differently.
See, you are talking about the what you call the properties, right? I am talking about the enantiomeric behaviors. Okay, the size that only will reduce the ring flipping energy. Okay.
So here we can consider both of them
Deuterium and
similar.
tritium cannot become that bigger in size so that it can change the amine inversion by 1 kilocalorie, 2 kilocalorie to 23 kilocalories. That's not possible. Okay.
Yes.
Sir, in case of the third example here, 12 kilocalorie, if in place of CH3, if there is something bulky group, can
definitely.
say that the result will be same, right?
Yeah, it will be chiral. Okay.
No, I think in the case where there is H and B, hydrogen and deuterium with nitrogen, and the third group is a
No. The result will be achiral like this only. That's why I said 2. Okay. Even what you are asking, I will draw it so that others can understand. Right? This is what you are asking, right?
Yes.
Yeah, this will be achiral.
Okay, sir.
Okay. Fine. Good. So we are nice. thing. So
molecule will be chiral.
It will be achiral, achiral, not chiral.
Okay. Yes.
Okay. Okay. Now we will go to the next interesting chirality. Okay. So far I have shown you a trivalent nitrogen. Okay. Now I will show you a tetravalent nitrogen. The good thing about tetravalent nitrogen is that you can, for example, I will draw two structures, then I will ask the question so that one this molecule.
The like the diagram
Okay.
is not visible. Like the
Diagram
old
is not
thing
visible.
only.
Come on, man. Now
I
I'm
mean,
drawing. Nah.
It is visible.
it is visible.
Come on, man. I'm drawing in PPT today so that it is good for everyone. Jara ye
Yes,
karte
so
rahe.
like the previous drawings
Yeah,
only is
now I
visible.
have
The
changed the
new one.
slide. Nah, I have not changed. Now it is okay. I'll change the slide.
No, sir, it's the same.
Might be
I'll
done.
rejoin again.
Yeah, yeah. Okay. Now these two compounds I have drawn, right? These are a tetravalent. So you can say that they are four. First I will ask you: is this a chiral or not chiral? These two molecules.
Carrots.
Come on, man. Be confident. There is no other.
Chirals.
They are chiral. Very good.
Chiral.
Because,
Chiral.
yeah, nice.
Both are
Nice.
chirals.
Nice, very good. So this nitrogen has four different groups. One, second, there are no hydrogen or deuterium or something like that. So these are all come to be chiral. Okay. Yeah, you tell me in this two, what interesting question can I ask from this two molecule? Can I ask whether this molecule is chiral or achiral? You will all answer, right? What interesting I can ask from these two molecules? You tell me, you frame a question, which will be interesting.
Which of the molecules
Number of
show
steroids.
inversion?
It can.
Come on.
So whether they will show amine inversion or not.
Amine inversion, no. That you are coming there, but can I be more? Can you reframe your
Stereogenic
question?
centers will be present in the two molecules.
Stereogenic centers, that is there, nitrogen, that you can easily find out.
It can
Number of
form. So it
stereoisomers.
can form their enantiomeric pairs.
Excuse me. Number of stereoisomers.
No. That is all easy, man.
Sir, in the first question, the ring is considered to be one molecule. Then why we are calling it chiral?
Ring is not considered. Ring is not considered. Come on, man. You have to see only this part, okay? Because always you have to know this ring cannot be in like this. This is cyclopentane ring. This you have different shape like this, okay? Envelope structure. I will teach you this one, okay? This will be envelope. So they have four different substituents. This is one substituent. This is one substituent. Okay, this is an envelope structure. It's not like what you. Hey, that's all. That's the interesting question you can ask. Come on, man.
So you can ask about
Sir, what
resonance.
if we remove the double
ring.
first molecule? Is that it?
If I remove the double bond, then it is not chiral.
Okay, yes.
You can
Because
ask
all are
question
four
about
different
resonance.
That's why I
like,
kept the double
Yes,
bond.
when the resonance occurs, what happens then?
Uh-huh.
So you can ask questions about the resonance structures in the molecule.
This is what now you guys are going away from the topic. Okay, so I can one guy said nice question. I mean inversion. So I can say that. See how I am making the same, and I'm trying to understand. Did you know the concept? I will ask now. Among these two molecules, whose enantiomeric pairs can be separated easily? You are getting my
First one.
question? Huh?
First
So
one.
the first
Ring.
molecule.
Yeah, that is what we are learning now, right? So this 1 and 2 whose enantiomer pair can be separated easily. Easily means, right? So what, 1 or 2?
One.
Why? Now the question comes why, right? Yes.
One
because
doesn't
there
show
is fatigue.
inversion.
Yeah, what? Yeah, you have to say that, sir. In one case, first it is chiral because it has 4 different nitrogen. Second, you say, sir, the ring is making a conformational locking, right? It's locked, so that I can now easily R and S can be different. It is conformationally locked, so there is flipping of nitrogen will be not there. It's locked there. That's why both the isomer you can even easily separate them by using distillation technique, or you can crystallize them. Okay, that's how it is. In this case also it is separated
The
same way.
the enantiomers can be separated by
No,
distillation
no,
or
no, no,
this
no.
way.
I'm telling. Okay, it is very good question. Enantiomers, how they are separated, pata hai? You have to attach them to a diastereomer, then you separate, crystallize out, then you remove the diastereomers. I will give that example. Okay, that's why I said what you said is really right. Enantiomers cannot be separated in that way. What we'll do, we will attach a diastereomer molecule, then we crystallize, and then we remove the diastereomer molecule. By the way, we can separate the enantiomers. But this can be easily separated in that way because it has conformational locking also, right? Because the ring is helping it out. So can I ask like that? Or you think can I ask in that way? Reasonably good question, right? Or not?
Yes, sir.
Rather
Yes.
than asking them a chiral or a chiral.
Yes, sir.
Hey, you
Sir,
guys
in
are,
second,
huh?
will there be anion inversion? In second one,
Huh?
will there be anion inversion?
Yes, yes, yes. Whatever you said is right. So can I ask in that way? Right now I know the concept, right?
Yes, sir.
So any doubt with nitrogen? No doubts, right?
Sir, in second question, if we attach pH directly to nitrogen, then
Yeah, then it is different story. Then as such it is different. pH means see you are talking about this molecule. That will be not chiral at all. Okay. You will be having something like that, no? Or you want to attach like this phenyl. This one, right? This one you are
So
asking, right?
you said that
But
the
that is this
general
is in
rule.
planar, right? So there is no problem here. This is more like a planar. So
So
the here
you said
also
the
flipping
general
will be
rule
there.
is
Yeah.
that if, so if the general rule you said that if two or more hydrogen atoms are replaced by carbon, chlorine, or bromine like that, then we will not have inversion as such. So why we are having inversion in this case?
What we are talking? I'm not here. What inversion we are talking about? This is not inversion, right? This is for four different atoms. This is chiral as such. Where the lone pair of electron here? This will be
So
RNS.
this
Okay. This will be dextro, levo, R or S. It will happen. Okay. That's
sir,
why I
if
went
we,
for a tetravalent carbon.
sir, then which will be easily separated one and two if we take
One,
directly
one,
pH.
one, one, one. One will be easily separated because this will always have a rotation, conformational ring. All things will happen for this. Okay. But here it
and
is
so
not. It is
it's
locked there.
still so
Yeah.
in
Go
the
ahead.
second case it is still occurring, but
Hmm.
the rate is lower, so that is why it is
Yeah.
still chiral, but
Yeah.
not
Yeah.
separable.
Yes. Definitely, these two are chiral. Hey guys. Hey, come on, man. These two are chiral for sure. I said that. Can I ask a question like this because it will be boring to ask, nah? For a IITN, is this two are chiral? You will definitely write this two are chirals. But I wanted to make the question a little bit interesting. I said among these two chiral molecules, which enantiomers can be easily separable? So I am little bit making little so that I see that whether more understood the concept. Okay, that's why, right now.
Yes, sir.
Sir, will the first molecule can undergo amine inversion?
No, 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 no. There is no amine there. No? It's a quaternary salt. No lone pair of electron.
Okay.
Hello, sir. I had a doubt in this slide.
Was
Sir, sir, if both of them do not undergo amine inversion because it is N
yeah,
plus, Then
Yeah.
what is the difference? Means they both are chiral, and
Yeah.
what effect will the ring have?
Yeah, ring will have this locking effect.
So
Okay.
then how it will ensure easy separation?
So can you please elaborate the locking effect one?
Yeah. Don't worry. I will take this conformational locking, right? In conformations area, I will explain you completely on conformational locking. Don't worry. Okay. I will definitely explain conformation locking is there in conformation chemistry. Don't worry. There we have a lot of examples I will explain there. Now you understand, for now it is conformation. Okay. I will explain that in detail. If I didn't explain, you let me know. Clear?
Okay.
Yes.
Sir, even if we remove the double bond, will it be the same?
No. It will not chiral at all. Where the chirality comes from? No chirality there. Okay? Same atom हो जाएगा ना?
And say if you remove the methyl and ethyl into hydrogen and deuterium, then
Yeah, then it is not chiral at all. Why we have so much confusion? It's not chiral at all.
Sir, if we replace double bond to the 3
See,
carbon,
if you keep on asking this type of question, then I cannot go forward at all. Okay, we should have doubts which should be clarified. But you say that sir methyl ethyl को hydrogen deuterium से replace करेगा तो chirality नहीं रहेगा, जरूर नहीं रहेगा, because it is, I have told by first definition itself, it is not there, right?
So, just a request, sir.
Yeah.
Yes, sir. So can you please upload the PPT after the class?
Yeah, sure. I will definitely upload the PPT of stereochemistry once the class is over. Don't worry, because I have not finished at all, na? Okay. Now, can we come to the sulfur? Nitrogen we have seen. Can we come to the sulfur now? Hey, sir, if you have asked some question, if I have said sorry, please ask questions, okay? But sometimes it will be good that if it is nice, okay? Don't change the molecule and ask that. That will be going for a representative example. Then everyone will ask questions. Then it will be more like a solving. I have to cover the syllabus also. That's why I said, okay, fine. Now, can I go to sulfur ka? Okay. Please ask questions, which should be good to interact. Okay. See, in exam we are not going to give you lone pair. Okay. So your molecule will have SCH3, pH, and H only. So you should know that it has lone pair. Okay. In exam we won't draw. Fine. Is this molecule can be called chiral? What happened?
Yes, sir.
Yeah, come on, man, answer. I said
Yes, sir.
Yeah, this molecule can be called as chiral based on what definition? One, it has 3 different substituents or groups attached to the sulfur. The second is that you have only one, right? Others are all methyl and phenyl. So both the definition sets properly here. That's why I'm calling this molecule as a chiral. Very good. Now we are there. Okay, for example, can we call this as a chiral? In exam, I am asking this question, okay? Can I call this chiral? No, sorry. No, right? Okay. Very good. Now, can I make this CH2 CH3? Okay, it's not methyl, it's ethyl. Can I call this chiral?
No.
No,
sir.
Why?
Still no. Sir, if sulfur is
Yes,
the
sir.
sir, if sulfur is the stereo center, then it is sp2, and there is no carbon that is stereo center. It's like chiral. So all
No,
carbons.
I'm talking only on sulfur. Is this sulfur can be called as a stereo center?
Sulfur is sp2.
No.
Yes, sir.
No, we should be clear. See, there is no doubt in, we should not play yes or no. Then it will be tough for you to write in the exam. Is this molecule is chiral or not? That's all I'm asking.
No, sir, it's not chiral.
No, sir.
Why? The
Sir,
rule
because
says that. The rule says that. What are the rules? The rule says that it should have different substituents, right?
sir,
Yes
it
or
should
no?
not also
So
have the
it should be
symmetry,
sp3 hybrid S2.
but
Hey, what
this
happened?
molecule has a symmetry, like a plane of symmetry that will cut right to the molecule. So it is
Huh?
not.
The rule says that is to have different substituent. It has a different substituent. 1, 2, 3. Okay. Why you are saying it's not chiral?
But it should also be sp3
sp3
hybrid
hybridized,
the
sir.
molecule.
It is planar
Hey,
molecule.
that is only for the carbon atom, right?
State as lone pair.
Yeah. Why you are okay? That's what I just drawn this molecule. It has lone pair.
Yes, sir.
Yes, sir, it has.
Yeah. Then is this molecule chiral or not?
Yes.
Yes, sir.
Yes, sir.
Now you say yes. Come on, man. So far you were saying no. So your 1 mark is gone now. So that means it's very clear that you are not going to go with the definition. This is the problem happens when you say yes or no, right? So you first apply your definition. Your definition very clearly says, that's why I said in exam I will not give you the lone pair at all. I will draw the molecule in this way only. You should know that there is a lone pair. So you think that I will give a lone pair here in the exam? Then it will be 8th standard question. Nah? So you think that there is a lone pair now, and the rule for me very clearly says that it should have 4 different substituents. It has a very good 4 different. Huh? Yes, sir. I'm not able to hear you.
Yes, sir.
So the molecule should be chiral, right?
So can you explain it again?
Yeah, the same definition. Can you fit your definition? The one who asked me the question. What is the definition says? Tell me. Hello? The one who asked me the question right now. Yeah, we are just finding out, man. Don't worry.
We have to have 4 different groups.
Yeah. Are they there? Are there?
Yes, sir.
Then is there is any small atoms like hydrogen, deuterium where it can flip or whatever it happens? Is there?
Yes, sir. My confusion is clear. This is tetrahedral. Yes, sir.
Yeah, it's a chiral, right?
Yes, sir.
Yeah, that's all. That's where I wanted you to redefine the definition. Okay, that's very important. Don't go
I
with
was
the
thinking like this is planar molecule. That is why I was.
yeah. That is what. What is you guys are completely right. This happens in the exam. That's what I'm saying. When I see in the exam question paper, this will be straightforward. We give you, but I think out of 100, 70 students write wrong. I don't know why. When we give sulfur, phosphorus, and nitrogen, I think 70 students write completely wrong. That's why I'm stretching more on this class. I don't want even anyone to lose even a single mark in my class. Everyone should get completely full mark. Okay? That's why I'm putting so much of stress on this. Any doubts, sir?
Yes, sir. No,
Are
sir.
we clear? Are we clear?
Yes.
Okay.
Yes.
Then we'll go to now another system, which is this is phosphorus. My P is so bad. Okay, now it is okay.
Sir, I had a question.
Yes, sir.
Sir, like nitrogen inversion, like nitrogen as amine inversion, does that?
Yeah, all.
happen
Yeah,
with,
sulfur also does. Phosphorus also does. Okay, definitely it does.
So the same
So
rules.
will there be
Yeah,
changes
yeah.
in energy of or the
Yes,
barrier in
definitely,
this case?
definitely. So that's why I said use the same rule. Okay. Same rule. Okay. There is not much difference in the energy. If the nitrogen sulfur invention is only 1 kilocalories, that's all the difference. Okay. For example, the question you are trying to ask is this type of question, right? This
Sir,
is also
one
has
more
3
question.
kilocalories per mole. Yeah.
So in the previous question we had like double bond with O, which means there was a pi electron cloud there. So will not pose any. Yes, sir. This one.
Yeah.
So,
Yeah.
so there is a
No, no,
pi
no.
bond also.
No,
So
no,
will
no.
that
It
not
won't. No,
restrict
no,
anything?
no. Don't worry. It won't do anything. Okay.
Yes, sir.
Don't worry. That's why I took that example. It won't do anything.
Yes, sir.
Okay. So now leave this compound as such because that was for the. Oh, sorry. Is this molecule is chiral? CS2, CS2, CH3.
Yes, sir.
Yes, sir.
It's chiral, right?
Yes,
Yes.
sir.
Yes.
Okay.
Yes, sir.
No doubt. Okay, very good. It's chiral. Okay. Now I will write another molecule. Is this molecule is chiral?
No.
No, sir.
No, sir.
All are clear? Any doubt?
So what is the substituent like oxygen oxide
Two
only?
oxygens, three oxygens, phosphates. Okay, these are phosphate anions. Huh?
No, sir. It's not chiral.
It's not chiral. Okay, now you tell me. I want to make this molecule chiral. What I
So
can
we
do?
have to add a different substituent on oxygen.
Without changing the substituent, I have to make this molecule chiral.
Like, sir, what are we allowed to do, like, to the molecule?
You can. I want the same atoms. Okay, that's all.
We cannot add anything.
You can add anything you want, but the atom should be same.
So like
If you,
to
you
the
are,
oxygen, one of the oxygen we can
By
add
adding some hydrogen and
deuterium and the other.
Join those two oxygens to form a ring.
Go ahead, go ahead. Someone
So
said
to
they will
the
add deuterium.
one of the yes, sir. To one of the oxygen we can add a different substituent.
Deuterium, why deuterium? Man?
I said different
Any
substituent.
substitute.
No, without changing the
It's
changing the
ONe
atom, I
can
am
do
asking.
OET.
Without changing the atom.
Sir,
Like
one
same
oxygen
we can
replaces
do
with OH.
OET.
One oxygen to OH.
Sir,
And
bond
you want
between the two oxygens.
one? What you said? Hey, come on, man. Simple. What I will do, Pata? You want to tell me the answer?
So the two oxygens can form a
like
bond.
Sir, the two oxygens can be bonded.
Bond this like this bonded. Then chirality comes. Then it won't be.
No, sir. Even then, current.
No, sir. It
Yeah.
won't.
Sir,
Then it will be again.
peroxo bond kind.
Huh?
Oxygen
Because
bonded
on
but
either
not bonded to
PO
phosphate.
bond will remain.
Yeah, that won't change.
On concentration
Sir,
bond
Can I
remain
make
OH
a
both
simple
cases.
thing?
OH and OD.
Why OD? Why cannot you make this O16 and this O18? Why only hydrogen and hydrogen as a isotope labeling?
But how will we chemically do that, sir?
Yeah, it is easy. You can do that. Okay, we have labeling. That's how we can label. Labeling, you have good reactions to label things. Okay.
So, I mean, from this molecule, from the initial
Yeah,
molecule, come
you
to
have you have this replacement labeling replacement isotopes experiments are there. Many you can do that. Very nicely you can do. But not all the molecule will be converted. Only 10% will be converted. That you can isolate, or you can use it for chemistry. Don't worry about the synthesis part. Okay, but it is doable. Is this molecule is chiral or not?
yes, sir. This is correct.
Okay. See that. So I have shown you all the tricks now. Okay, how to make things chiral chiral, right? Are you happy? So what we have seen, carbons, and we defined it as the carbon having 4 different groups, as the definition of chirality origin, but now our definition is completely changed. Our definition is that any atom, okay, can be made as a chiral or stereogenic, whatever it is, if it is attached to a 4 different groups, and it should be that it should not be hydrogen. The 2 hydrogens cannot be there, or hydrogen isotope should not be there. That's how our definition is now turns out to be. So it can be nitrogen, sulfur, phosphorus, germanium, whatever you put in. I am ready to answer, sir. Is it clear, sir?
Yes, sir.
Any doubt? If everyone will get full mark, right?
Yes, sir.
Yes.
Are you okay? Before that, are you guys are enjoying the class, or it is boring? You can give me suggestions.
Yes,
Sir,
sir,
if it is
enjoying.
boring,
Yes, sir.
just
Yes, sir. Enjoying.
okay. If it is boring, you can say me, sir. You can do like this guy.
Sir, in the previous example, can it be go on under resonance?
Resonating structures are not there. Na? What is resonating structures? It won't resonate. Okay. It's a phosphate anion.
Sir, hello.
Yeah.
If
Yes, sir.
either of the resonating structure is chiral, then we will call that molecule chiral or
Yeah.
achiral.
It will be chiral. See, for example, in a given molecule, there will be n number of enantiomers, n number of diastereomers. Okay. But that's why I'm saying it is a static stereochemistry what we are talking about. We are not talking about the dynamic stereochemistry. So in your so we are talking only the static state of a molecule. That's why I defined in the first slide what is static and what is dynamic. Right now we are talking all about static stereochemistry.
Yeah. So static stereochemistry, we don't have to consider resonance effect.
Don't consider.
Okay.
So good class, man. You guys are nicely interacting with me. I am also enjoying the class, and I'm teaching you more. Good. Shall we go to the next topic then? So everyone will get full mark in chirality. Okay?
Yes, sir.
You want to study again? No need, right? Now you can remember in mind. Okay. Okay. The next thing, what I'm going to
what give us some practice questions too, it would be very nice.
Definitely, we will see. That's why I asked the TA to do. If it is not, you let me know. Tomorrow you have a TA class, okay? There I will ask them to. They will be doing some problems. If it is not there, then I will. We have a lot of times. We will definitely do the problems. Okay? Okay.
Yes.
The next thing is that which I want to, at least which we want to discuss, is enantiomers. Okay, it's a very nice word because after chirality, we have to talk about enantiomers. Okay, so the definition is as simple as it is. A pair of molecules that are not superimposable mirror image of each other. What is the definition? So enantiomers. A pair of molecules
Superimposable.
Non-superimposable. Very good. Non-superimposable mirror image, right? Sir, you guys always do this mistake, sir. You always remember this word non-superimposable, but most of the time you forget this word that it should be a mirror image. See, one time, just for fun, in a class test, okay, I asked this question. Okay, these are different substituents. For example, R1, R2. Okay, this is R3, R4. This is carbon. R3, R4, and then OH. And then I add a CH3, then C, R1, R2, R3, R4. And instead of OH, I made an amine here. And I asked whether this compound is an enantiomer. Okay, I made it this R1, R2 properly that they are enantiomer. Like if the S comes here, R comes, S comes, R comes. I made it like that. And I said that whether these are enantiomer. All of them wrote, not all of them, like 80% of the class wrote it is enantiomer. Is this an enantiomer?
No, no, sir.
No, sir, it is not mirror image.
It's not the same.
Yeah,
The molecule is not same in fact.
yeah, people forget this. I don't know why, because I know that you guys are very brilliant. There is no doubt about it. But I don't know why in the writing in the exam, it becomes lethargic to see the molecule or what, I have no idea. Okay. Your mind, once we say enantiomer, immediately you don't see this last functional groups, you immediately see the R and S and you say, okay, superimposable, non-superimposable, you finish it up. But finally, it will be two different molecules. Okay. So please give that attention for this definition. It's a pair of molecules that are non-superimposable mirror images. Right, sir? That's why I'm always define things properly. It's a non-superimposable mirror images. Okay, now, yeah, fine. This is one of the example. Fine. I've given you A, B, C. Is this all molecules are enantiomers or they are not?
B is alone enantiomer.
Only B is an enantiomer.
See, I understand. I have not defined it. The definition is very simple. It should be a non-superimposable mirror image. That's all the definition is. Now, you tell me, because you said I know the definition. That's why I put this 3 molecule and I am asking which is enantiomer.
Each pair
Sir,
is
A is not.
Each pair.
B and C.
A and C are not enantiomers.
A and C are not enantiomers.
So B
Why?
and C are enantiomers.
Look into carefully. No? Why?
B and C are
Yes,
enantiomers.
Yes,
Sir,
B
all
and
are in.
Sir, all are enantiomer.
Yeah.
Yes, sir,
See,
all are in.
this is what the problem comes. That's why I said that confidence of definition doesn't work here.
Sir, B is not enantiomer. A and C are enantiomers.
Sir, A and C, shouldn't they be diastereomers?
No. I am not asking any diastereomer. So don't jump to that. Okay. We are now learning only enantiomer. Okay. Now, if you have this ABC, why I gave this problem, first you should think. Okay, why Sir has given this problem? To find out whether I know the JE question or not. So there is no reason for this, no? Whether I'm JE. I know that in JE you have studied enantiomer, diastereomer. Still, why I am giving this question to you? There should be something meaning, right? The meaning is that, sir, please don't go with the structure directly. Okay, we can draw the structures in ChemDraw in different ways so that we can ensure that you end up in getting a wrong answer. Clear? So if you want to jump into enantiomers and diastereomers, the first rule is that see whether it is R or S configuration. Okay, then only you come to a conclusion. Please don't jump directly. That won't work at all, because I can draw molecules in different fashion and make you to end up in the wrong answer. Pata hai? That's why I gave the structures. So what you have to do, just by seeing the molecule mirror image and then superimposing, doesn't work that easy. I can draw this dash wedge form in such a way that you end up in confused. Okay, so ensure that, because you will have a lot of time. It's not like IIT JEE, we are giving you minimum time. You will have a lot of time. So ensure that it is an R and S. Then you ensure that it is an enantiomer or diastereomer. That is a pin. That is a pen point you have to take care. That's why I put this slide. So, what is the definition? That's why I said this is the thing to watch. So, what is this? So, the definition says that. So, I have told you two things now in enantiomer. What are the mistakes you guys do? Enantiomer, you think like it is a mirror image. It is non-superimposable. It's a non-superimposable mirror image, but you forget that mirror image. Secondly, you jump on this overlapping these molecules directly from your eyes. Please don't do, because it is very easy, end up in getting a full mark out of it. by using RS nomenclature. Okay, these two things where you go wrong in enantiomer. Other where you go wrong, other things. Guys, are you listening?
First, we need to see it is chiral center or not.
Yeah, that is true. That is true. Other things I will say, if the molecule is enantiomer, this is other two things where you go wrong. For example, you see this molecule. What is this molecule as? So you should see whether the molecule has plane of symmetry. If the molecule has plane of symmetry, then there is no meaning of talking enantiomers there. Please don't do that. Okay? For example, this molecule, you take this molecule will be enantiomers. Is this is enantiomer? This has an enantiomer? No, right?
No, sir.
No,
Because it has a nice plane of symmetry. But immediately, I don't know, once in this exam you jump on, you take this molecule. This has a nice plane of symmetries. These are all. So look for plane of symmetry. If there is a plane of symmetry, please don't talk about enantiomers. We will definitely give you a molecule where there will be a plane of symmetry. And we will ask you whether it is enantiomer or diastereomer. You will immediately write enantiomer. You will forget to see that there is a plane of symmetry. Okay? That is the second thing where you do wrong when you look into enantiomer. Third thing. What is the fourth thing where you go wrong? You again miss the element of symmetry. That also you miss. You miss element of symmetry. If a molecule has an element of symmetry, then it is not going to be a enantiomer. Okay, I will show you one example where we sort of ask regularly and people write wrong. Okay, I will give you one compound. Just a minute. I will, okay. Just a minute. So what are the four things? Guys, are you guys are there?
Yes,
Hello?
sir.
yes.
What are the
Yes,
four things?
Superimposable mirror images, plane
Yeah,
of
I will.
symmetry, center
Very
of
good.
symmetry,
Mm.
and the fourth
Four
thing is
things.
that
Okay.
we have to check the R and S configuration.
Yes. So the four things where you go wrong in enantiomers. The first thing is that you don't see whether it is a mirror image. The second thing is that you just overlap the molecules. Don't do that. Check whether it is an R or S configuration. The third thing that the molecule should not have plane of symmetry. Check that. And the fourth thing is that the molecule doesn't have element of symmetry. Sir, please, sir, check all these things before you end up doing anything wrong. So why I am saying, I gave this example in previous exam for previous batch. Okay, you see this. I teach them
Sir, what
nitrogen.
is having axis of symmetry?
What?
Axis
Yeah,
of symmetry.
I'm just drawing. I'm drawing that only, element of symmetry. Okay, I gave this molecule in previous exam and asked whether this nitrogen is chiral or you have any enantiomer for this nitrogen. Is this nitrogen is chiral?
Sir, chirality will be different for the molecule, but the molecule has a center of symmetry.
Very good, very
So
good.
nitrogen
Very,
can be a stereo center, but the molecule is not chiral.
very good, very good. Good. This is what, please, Sadit, the question. Okay. I asked whether this molecule can exhibit enantiomer, or I asked whether the molecule is chiral. Many people wrote this molecule as a chiral element. Because they said, sir, you only teach me in the class that you see this nitrogen, it is like 4 different, and if I put a lone pair, there will be no ring flipping, everything. So this is, come on, man. Yes, I teach you that. But you see the element of symmetry in this molecule. You take this point, you go this direction, you go this direction, you go this direction. It all same atoms, same substituents. So it has a nice element of symmetry, or center of symmetry, or inversion center. Then now you say that this molecule is chiral. That's why I'm saying, and there is no enantiomeric pair. What enantiomer you are writing on this? And you will write, see, again and again I am repeating the class. I don't know, again, when I keep the same question in a different fashion, you will write the answer. You will write enantiomer of this, or you will write that this molecule is chiral, and whatever you will write this. Again, I am repeating, sir, please don't, once you know the answer, you should not do a silly mistake. See, if I don't know the answer, it's well and good, man. I'm happy. I can come out from the exam and say, I don't know the answer. Nahi pada tha. Okay, okay. But if I studied and if I don't know the question answer, then it is doing silly mistake and getting out of it. I think that is not, that is a big sin. Okay. So the 4 things you will watch when you are looking for enantiomers. 1, it should be mirror image. 2nd, it should be, you should look into RNS. 3rd, it should not have plane of symmetry. 4th, it should not have element of symmetry. Then only the molecule you will consider them as an enantiomer. Otherwise, you will not look into the enantiomer of the molecule at all. Clear?
Yes.
Clear or not?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay, I'm not wasting your time, nah?
No.
No, sir.
Okay. Because I want to ensure, because you guys didn't have lunch, breakfast, and you are sitting in my class, I should ensure that your 2 hours is worth. Okay, it's not boring. You learn something meaningful. You need a break?
No, sir.
Excuse me, sir.
Yes, sir.
No, sir.
No, sir.
Okay, thank you. Then I
So
will
why
continue.
it happens if molecule has center of symmetry, then it will be optically inactive?
Yeah, because if you rotate, it will be the same molecule. It will be identical. OA molecule है वो. तो घुमाएगा
So
तो.
basically,
It will not be a
like
mirror
even
image.
if it
It
has
is.
a stereo, so if it has a stereo center, then one part of it will try to rotate the plane of polarization, but the other part will
No, then it will
push
cancel
in the
each other.
opposite
Then it will become 0 degree.
Yes.
They will cancel, na?
Yes, it's like.
Okay. Yeah. Now at least this he is remembered. Okay. Nice, man. Before coming to RS, I thought I have to discuss that. Okay. Fine. Can we get into RNS now?
Yes, sir.
Yes. Very good.
Yes, sir.
Right. Now, in RN and just configuration, before getting into RN, yes, I want to tell the origin of this also. Okay, that is very interesting, and you might end up in getting some objective questions from there also. Okay, how? See, do you think how this scientist got into this idea of
Excuse me, sir.
enantiomers? Huh?
Sir, I'm asking that if molecule has axis of symmetry, then will it be chiral or not?
What axis of symmetry? You cannot have C2 you should have inversion of symmetry. That's what. Okay.
So I think he's talking about the alternating axis of symmetry AN type.
No, I'm talking CI. Okay.
Yeah.
I'm talking CI. Okay. Central inversion of symmetry.
Sir, won't we check for AN then?
Don't check. 120, 130 पूरा नहीं आएगा. Yeah. Fine. Now can I go for R and S? Okay. So how you think that scientists would have came to an idea about 2 enantiomers? What was the lead? Which gave them a lead that these 2 compounds are different?
The difference in properties, like chemical properties.
That was the first identity, or Before that, what was the first identity?
Physiological effects like the
Silence.
thalidomide and all.
No. That
So
was kind
different
of that
angles of
Optical activity.
very good. It's optical activity, right? Yeah, this is a very important thing because this misleads many people. I want to remove that mislead or misnorm, whatever it is, which we have in our mind. Okay. So the scientists were looking into the optical activity of the molecule using a plain polarized light. Okay. And they found some of the molecules were able to rotate the or turn the light in a clockwise direction, and other molecules were able to turn it in the opposite direction. The one which was able to turn it in the clockwise direction, they named them as a dextro compounds. The one which was able to turn it in the anti-clockwise direction, they call this as a levorotatory. You guys know that, no? Dextro.
Yes,
Yes, sir.
And this you have known that. Okay.
Yes.
Yeah. Now where the misnorm comes here is that people are thinking the same way for R and S. Many of these guys are thinking like that this dextro goes to R and levo goes to S. No, sir, no, not at all. If R compounds, many people think like based on their nomenclature, they are thinking that R compounds are able to turn the plane polarized light in clockwise direction, and yes, we are able to turn it in the anti-clockwise direction. No. Only the dextro compounds are able to turn the light in the clockwise. Levo is able to turn it into the anti-clockwise. Then where this R and S, what this R and S does? R and S definitely of a given compound will have different direction of turning the light for sure. That is the first thing. R and S of a given compound will have different orientation of light. For example, I take a ibuprofen or any amino acid. I take a simple amino acid. R amino acid can turn the light in the anti-clockwise direction, whereas the S amino acid can turn the light in the clockwise direction. So, or it can be for other amino acid, it can be other way around. So, R and S is not going to go for a clockwise or anti-clockwise. R and S is going to go only for the change in the direction of the light, not like dextro and levo. This is very important. We ask this in objective questions. You guys still do the same mistake. We say the plain polarized light is optically turned in a clockwise direction. R compound, S compound, dextro compound, levo compound, R and S compound, none of the above. So many guys write R and dextro. I have seen the objectives answer. Many write A and D, A and C. What is A and C? R and dextro compounds. No, not at all. It's a completely wrong. Okay, dextro and levo. Dextro only turns the light in the positive clockwise, levo in the anti-clockwise. R and S can be any way, but for a given compound, R and S should turn the light in the opposite direction. That's all. Clear with this, Miss now?
Yes, sir.
Clear, sir? Or any doubt with this? Because you sometimes we ask objective questions from the air only. Doubt nahi hai na? So I can go forward. Okay.
Yes, sir.
Okay, fine. Now for R and S, we can look into the sequence rule, which is by Coe and Ingold. The rules, I know that you guys pretty well know the rules, so no need for better definition. But anyhow, I will just remind you again. The rule says that you assign the numbers for the substituents or the group based on the atomic number. That is the first. Then other things. Then you make it clockwise or anti-clockwise depending on the directions. That's all fine. That is, if you make it as a clockwise, then you call them as what? Clockwise is what? What is clockwise? R or S? This is only for nomenclature. I am not talking with the light. Okay, it's only nomenclature. So if it is clockwise, then it is R. If it is anti-clockwise, then
It
it is.
depends on the fourth group also.
Yes, sir.
Yeah, fine. I will come.
If it
Definitely, I
is
will
on the
come there.
solid wedge, that will be
Yeah. Sorry, sir. I will definitely come there, but I will finish off this rule. Okay, keeping the hydrogen away from this. That is all fine. I will come there. Don't worry. But you assign them the number and you check whether it is, as my friend says, that keep the hydrogen away from you, and you see that whether it is a clockwise or anti-clockwise. If it is clockwise, then you call them as an R, and if it is anti-clockwise, it is a S. Fine. This rule I think you have studied in and out. I am not going to explain this more. But what is new I am going to tell in this rule is that two things very important in this rule which you should understand. One, if you have hydrogen, deuterium and tritium, what will be the numbers? Come on, man. Hydrogen.
same only. Atomic number is same.
The heavier isotope will have higher priority.
Very good.
Number is same, that the mass.
So tritium will be 1, deuterium will be 2, and hydrogen will be 3. Right?
Yes, sir. Yes, sir.
If it is labeled oxygen atoms,
So higher.
480
will be
yeah. Yes, very good. Lone pair of electron. Lone pair of electron. Lone pair of electron, most of the time you can give them as the lowest. Okay?
Lowest.
Yeah.
Lowest.
Okay.
But
so,
when hydrogen is present, what will we do?
Lone pair only I will give the lowest one.
Okay.
Okay, that's why I took this rule, because I know you know the 1, 2, 3, 4 and keeping things behind and making it clockwise, anti-clockwise, R and S, you know. But what you have to remember is that you have to remember these three key things. One, if you have hydrogen, deuterium and tritium, you will go tritium 1, deuterium 2, hydrogen 3. The second you have to remember is that if you have a label oxygen, you will go with the labeling one. 18, 16 and 12 is there, then you will go for 18, 16, 18, 17 and 16 is there, you will go for 18, then 17 and then 16. And then the third one is that if there is a lone pair of electron, you better consider them as the lowest group. Okay? So these three things you have to remember in R and S. If you have not studied, if you have studied well and good, I am just adding this to it. Can you remember these three things? Okay. Friends, if you say yes, then only I can go.
Yes, sir.
Yes, sir. Please.
Fine. Now, how conventionally, if you present a compound is very important. Okay, for a RNS, most of the time RNS, any compound, most of the time conventionally we will present it either in a Fisher way or we will present it in a wedge and dash way. This is the two ways most of the time we present a molecule. Okay, in any books or any anything you will present a molecule in this. Newman projection is very less. That is only for when you go for a conformation. But in general, the projection will be in either in a Fisher or in a wedge and dash. So now we will see how we can understand an R and S configuration when it is projected in a Fisher form as well as when it is projected in a in wedge and dash form. Okay, Fisher projection is very simple. So Fisher projection is this. What it says in Fisher projection? I will take the pointer. Okay, Fisher projection. So this molecule is given in the Fisher projection, right? If this is given in the Fisher projection, it is very easy. So you can number them. So ethyl will be 1. So how you number this? Okay, I think
Chlorine 1, sir.
yeah, chlorine 1.
Chlorine 1. Normal
Yeah,
propyl 2.
propyl will
Propyl
be 2, ethyl will be 3. Then it will be what direction? What is this direction now? Is this a
clockwise, sir.
clockwise? Yeah, clockwise is R. And the main thing here to note is that where is the hydrogen?
Lowest point.
Hydrogen is
Vertical,
in
sir.
the vertical
Somewhere
lowest.
vertical
Yeah.
attack.
If the lowest priority group is in vertical, then you don't need to change the configuration. Okay? If the lowest priority group is horizontal, what will happen? Then your R will become S, or S will become R, right? It should
Yes,
be
sir.
other way wrong, other way round. Yes or no?
Yes, sir.
Yes, very good. Um, okay, so what I will do is that I will take a slide so that we will work on that. If you don't work, then there is no meaning of that. Okay, so if I take this molecule, okay, tell me what is this stereochemistry?
R.
No, don't tell like R or S. Explain me so that you help me out.
The tritium will
Number
be first priority. Deuterium will be hydrogen.
Deuterium
And
is
then that will be
Sir,
low.
it is not chiral, I think.
3,
Hello?
4. I'm right with the number or I'm wrong?
Excuse me, sir.
Right, sir.
It is not chiral, I think.
No.
No, it is
Leave over.
carbon.
It's chiral only, man. Why?
Sir,
not
It's
lone pair
center.
will.
It is carbon center.
no. Why it is carbon? I can put anything here. Okay, I didn't say it is carbon. Okay, don't worry.
Sir,
Right?
yes, HDT are there. You said two different.
Okay, fine. Okay, whatever is what my friend said is right. So my friend is saying no, sir, it's not chirality. Very good. I should accept that. Is this is chiral? No, na?
No, sir.
Okay,
No,
then
sir.
I should make this as CS2. Very good, man. My class is really good class. Okay, now can I go?
Yes, sir. No.
Very
Yes,
good.
sir.
Nice. This is very good. Whoever finds it's good. Good for him. Nice. Now, can we number it?
Sir, ethyl will be 1, methyl will be 2, and deuterium will be 3.
Lone pair will
2, 3,
deuterium.
4. Is my number is right?
Yes, sir.
Now direction should be what? You should be this direction.
Clockwise.
Can you please explain why the first one isn't chiral?
Yeah, according to our rule, what we said is that rule number 1, what we said.
The
Rule
different
number 2
groups
for
will be
nitrogen atom. This is chiral.
so due to inversion.
Yeah, that's what he asked me. Okay.
Oh, so is that okay? So here also it will undergo the inversion.
Yeah, come on, definitely, man. Right, that's what he was very sharp in finding out. Very good.
Okay.
Good. That's how I said, if you know the answer also, better think 2 or 3 times before you jump into it. Okay? Now what is this? This is clockwise. What it is clockwise? R, right? But where is the lowest priority group?
No,
Vertical line.
on the
Vertical
vertical.
means I have to change or I don't need to change.
So
No
don't
need
need
to
to
change.
change.
Okay. So the actual frequency will be R itself. Good. Very nice. Okay. So now I will take another molecule. O17, can I label it O17? Oxygen. This is a double bond oxygen, okay? This is OCH3. This is phosphorus. This is double bond oxygen, okay? Yeah, now number and help me out.
Sir, what you wrote just before methyl?
OCH3, sorry, OCH. O, this is O, oxygen.
Sir, O18 will be 1. O17 will be 2.
Among these two,
OCH3.
No, sir,
O?
then double bond O, because it will be like an O.
Double bond will be once.
Yes.
Yeah.
See, I am drawing for the structure which I have teached you for the chirality. Okay, so it should be double bond. That's why I said it should be double bond. Okay, you should not draw here, but I can put a double bond here. So what it should be 18, 7, 2, then 3, then 4. I'm right?
Yes.
Yes.
Any doubt with this?
Yes.
Wait, sir, I didn't understand why double bond comes before OCH.
First you will see the first atom, right? Then only you go for the second one, right? If you are not able to differentiate with the first one, directly connected one, then only you go for the second connected one, right? Yes,
Yes,
or
sir,
no?
but here both the
Here the
first ones are
directly
both the
connected
same.
one, SP, SP3, SP2.
Oh, got it.
Got it, right?
So SP2 gets priority.
Yeah, yeah.
Sir,
That's
we
all.
will take a
So,
pseudo
see,
atom. No?
yeah, you can do that. But SP2, see, that's why I'm seeing in one example how I am trying to build all the concept together to see whether you know everything. I give you this molecule. Now I will understand whether you know about chirality principle. And now I will understand whether you know about R and S. Same way I am bringing whether you know the concept of sequence rule. The sequence rule says that one after the another. Okay. And then I will know whether the labeling you will understand. So in a single molecule, I have defined all my definition and I summarized here. It's a very good example.
I have one
1, 2,
doubt.
3, 4. Can I finish this? So it is clockwise or anti-clockwise?
Anti-clock.
Yes.
Anti-clockwise.
So what is the? So it should be reversed or not?
Reverse.
No, but the reverse side horizontal.
Horizontal means reverse, na?
Yes, sir.
Yes,
So
sir.
it should be R. So I am done with it. Yes. Now you add some question. Go ahead.
Sir, like in double bonded or triple bonded cases, there can be two ways of finding. One is the hybridization we will consider priority according to the priority, and then another is the pseudo atom. So which one should we take? Because like in the pseudo atom, suppose there is a double bond CH2 and there like double bond C and there is a normal C and then some other group is attached to that. But if we take the
First you
pseudo
take
atom,
the first always give the priority for the double bond. Then you go for the pseudo atom. Okay? First directly connected should be given the priority. Then the second one, the pseudo one. No doubt with that. Okay, it is very clear. Okay. So मजा आ रहा है? ये problem. These problems are interesting.
Hello.
Yes, sir.
Yes, sir. Sir, that means if there is double bond CH2 and single bond OH, then would give priority to double bond CH2.
Hey, come on, man. This is what, man. You guys are. I am saying that First is what? First rule is that your atomic number that you cannot change at all.
Yes. Okay, sir.
Yeah, atomic number that is defined. That is the first rule. Second is within the atomic number where I have to give, right?
Okay, sir.
अब दो ऑक्सीजन आ गया तो तब किसको देना है? That's what I am talking about. Not about the change in atomic number. That you should not change.
Sir, also the same the case for isotopes. Means if there is double bond between. Okay.
Yeah. Everything. अच्छा है ना example, ठीक है?
हाँ sir.
Yes, sir.
Like that example, can I ask you in the exams? Hey, come on, you are not saying yes or no.
This one, yes, sir.
This type of questions can I ask in exam?
Yes, sir.
Okay, fine. Okay, now come to the wedge and dash way. I think this will be the last thing which we are going to learn. What's the time now, guys?
11:28.
Okay, very good. So this will be the last thing which I are going to teach in this class. Okay, wedge and dash, how to see that it has a peculiar way. See, most of the time what happens, you get wedge and dash form only in exams. Okay, because that is easy to draw in the question paper. So people, and in the book also, people give that. So we should give some importance here for the wedge and dash. So what I will do, I will draw them. It's better to learn by slides. I like this interactive writing rather than putting in PPT. Okay. So this rule I think you know, but still, I will again refresh your mind. So you have this compound. We'll take a simple one first for understanding how to convert this to Fisher.
Sir, have you changed slide?
Yeah.
So it is not updated on our MS Teams.
Not MS Teams. I was using only PPT.
Your whiteboard is not visible now.
It is stuck the way that you had last drawn.
Yes, sir. I can see the previous slide in which you gave example.
Okay. Just a minute.
I can see the new slide.
Yes, sir. Now we can see.
Now you can see, right?
Yes.
Okay.
Yes, sir.
Okay. Now how to convert this to Fisher? Okay, you guys know it, but still I will refresh your mind. Okay, so the simple rule is that take this one, which is your what you call as a simple line, okay, as your vertical line, COOH and CH3, that will be yours. And now you have to see the
diagram is stuck at one, like it is not progressive.
It's not going. Sorry, it's not there.
So it did not get fixed. It is stuck there.
Okay, I will just go back and just come again.
So maybe you can try stopping screen sharing and then try sharing again.
Okay. Now it is there? No?
No, sir, it's the same diagram.
Okay. Stop screen sharing. Stop. Now you can see anything?
No, sir, it's all black screen.
Now?
That screen is visible.
Can I see this? You can see the board? PPT?
No, sir, it's the screen is black.
Screen is loading, sir.
Loaded. Okay, just a minute, sir. What happened? Just a minute, sir. In this one, no, no, no. Stop presenting. My net is not working. Can you see now anything?
No, sir.
Black screen.
Black screen. Because I see
Yes,
my
yes.
PPT also.
No, sir, we can't see anything on the screen. The screen itself is not visible.
Okay, just a minute. What happened? Now?
No, sir.
No, sir, same issue. Black screen.
I think something happened. My network of mine is. So what I have to do, stop presenting and then go back and do it again.
And now we can see.
Yes, sir.
Now you can see.
Yes, sir.
Yes.
Okay, fine. Okay, fine. That means I will be starting again. So I will draw the structure COH, CH3, and then you have in a bridge form you have OH, and in the dashed you have hydrogen. Okay, fine. Now first we will try to convert to Fisher because Fisher is easy. So the goal is that you keep this straight lines. Okay.
No, sir, are you drawing something right now?
Yeah, I'm drawing something.
I think the screen sharing is stuck again.
No, I can see.
No, it is
Yes,
visible.
we can
It's
see.
already.
Acha, got it.
Just refresh your screens. Just a minute, sir. Just a minute. Now you see, check.
Yes, sir,
Now
it's fine.
it's visible.
It was an issue on my end.
Okay, fine. Now this is the more critical one, the one. So what it is easier, you always keep your dashed one, whichever side it was, just keep the side. Don't change the dashed group. Okay. In this case, the dashed one is hydrogen. Okay. Don't change the direction of it or which side it was. Now it is, for me, it is in the right hand side. So I'm not going to change the side of it. I'm going to keep this hydrogen like that. The one which is the wedge one, I'm going to change the direction on the other side. So then it should be OH. So that is the only trick here. Okay. The trick here is that the dash one will be on the same side. It won't be, you should not change the side of the dashed one. That is the only thing, the trick. Okay. So for example, I will give you another molecule. For example, we'll draw a molecule like this. So, can you guys OH? This type of questions comes in the exam. Now, what you are going to draw for this? The Fisher one. So in the exam, it will be like this only. So first thing what you have to do, you draw the hydrogens before doing anything. Okay? Just draw the hydrogens. Then which is the one without this bond? Okay? That you make as a straight line. So the CH3 and CH3. Now I'm going to talk about this chiral carbon. So the hydrogen should be on the same side because it is on the dashed one. So I'm keeping the hydrogen on the same side. The OH will be on the other side. So I'm going to place it on the other side. So in this case, what will happen? Hydrogen will be on this side. So I'm not going to change the hydrogen, but the bromine will be on the other side. So I'm going to keep the bromine on the other side. So if you want to change the wedge and dash to the Fisher projection, keep your dash on the same side where it is present. Don't change the side of the dash to one. Any group it be, the dash one should not change. Only the wedge side only should to change. That's all. It is as simple as it is. Okay. The another thing people always have a confusion here. If the molecule is given in this way, for example, people give the molecule in this way and they get confused. For example, I give this molecule CH3, CH3. You have a OH, bromine, chlorine, and you have again OH. So the way you should, this is in this direction, you have to make them as a straight line, right? Always the way you should look into it is you have to see in this direction. Okay. So this will be the head of the molecule and this will be the tail of the molecule. This people have some confusion in this. So if I draw this, this will be the head. So it should be CH3. This is the head part I'm drawing. Okay. So you have to turn like this. So this will be the OH and this will be the chlorine and this will be the bromine and this will be the again the OH and this will be the CH. You're getting this? So I have turned this from here to here to make it straight line. That's all. The hydrogens, now you draw the hydrogens carefully.
I could disconnect.
Fine. Now, how to make it to Fisher? Make a CH3 here. So I'm going to draw this. So I'm not going to change the side of the hydrogen. So hydrogen will be this side. The OH will change this one. In this case, the hydrogen side I am not going to change. Hydrogen will be here and Cl will be here. This case, I am not going to change the hydrogen side. So hydrogen will be here, bromine will be here. And this case, hydrogen will be in this side and OH will be in this side. Any doubt? Sir, any doubt, sir? All guys are there?
Yes, sir. Right. Hello.
Yeah.
Sir, the right side will be always head, or the direction will be given. Means which side is tail and which side
No,
is
if the
head.
direction is not given, you always keep the head on your right side. Okay?
Okay. Okay.
Don't change that if the direction is not given. Always your head will be right hand side.
So if there are different types of groups, wasn't there a rule like we keep the least, like most oxidized group on the top always of the Fisher?
No. Don't do that. Keep your head on that side, tail on this side. That is easier. Okay?
Okay.
Sir, this
otherwise it will be more confusing.
Is a convention or something.
We won't mention it. Okay? We won't mention it. We will see. We always keep the head on the right hand side of the molecule. We don't mention it. It is, you should understand that. Okay? We won't mention. It won't be mentioned drawing like this head and tail. Always head should be on your right hand side. Okay. Any doubts, sir? What happened? No one is there.
Network.
Network is not there. Okay. So Teams, we'll get to the Teams. So what, guys? So what we learned today?
Excuse me, can you go to the earlier slide? Means that one you have drawn.
You guys are drawing that. Oh my goodness, I have not saved it. Why?
Sir, means if the position of hydrogen depends on the drawing, sir, we can draw the dash in any direction of the line. Then,
No,
sir,
no.
Oh,
what position? I don't know.
Can you explain that example once again, sir?
Once again, the example. What happened? Okay. See, for example, you have this, right? So I have a CH3 here. I have CH3. Yes.
Yes, sir. It's visible.
Huh?
Yes, sir.
Okay. So I have OH. I have Cl. I have again, I don't know, bromo. Again, we have a OH here, right?
Yes, sir.
So I am going to look the molecule only from this direction. I will keep this as a head and this as the tail. Okay. I'm going to make this molecule straight now. Fine. So straight means I'm going to pick like this and make it straight. So if I make the straight, so it will be CH3. So here I will have OH and here I will have chlorine. Here I will have bromine and then OH and then methyl. Up to this is right?
Yes, sir.
Okay. Now
sir,
you place your yes.
I have in doubt, sir.
Yes, sir.
Sir, in this type of like we are going from tail to head. Sir, is this always be like nor in any case like in nomenclature like the one should be on the top and the like the last carbon should be on the tail.
See, this is for example, this system will change only when I go for biphenyl. Okay, there I will give you the rule. Okay,
Sir,
not for this,
like
not in not in this
nomenclature, then
yeah.
the from the tail part it should be one.
That is for the biphenyl and other systems. Don't confuse that. That I will teach you when I take tomorrow class. Okay? For this type of system, this is a simple rule. Don't confuse, then you will end up in problem. Okay? So these systems, keep this right hand side always in your head and this as a tail. Now turn the molecule, you have this one. So you have hydrogen is here, hydrogen is here, hydrogen is here, right?
Yes, sir.
Hydrogen.
Now,
Yes.
my question was that why are we drawing hydrogen on the same side as the dash? Means we could have drawn hydrogen on the opposite side of the main line. So then that would have changed because that would have not changed the diagram, but that would have changed the Fisher projection.
No, why you are drawing on the other side? Because when you draw, this will be the other atom, na? This is on the other side. So this hydrogen should be like this only, na? Tetrahedral, na?
Yes, sir. I got it. Okay.
Okay. Fine. Any other doubts, sir? No doubts.
Sir, why did you draw the hydrogen set? Can you explain?
Later, come on, later you won't end up in getting that tetrahedral because that methyl is already in this direction. Methyl, methylenes are this way, and then therefore you have OH hydrogen like this. Okay, for example, you have methyl here. Huh? So I have my OH here. I already have my methylene here, right? Yes or no?
Yes. Yes, sir,
And then Then how I can draw it? Then I have to put here for getting a tetrahedron.
But if methyl will not be there, then we have to put a
Yeah,
hydrogen inside.
then you have options. Then the option comes. Okay? Don't worry.
Yes.
Yeah, okay. Fine. So, so what we learned, man, can we summarize in just a few seconds? So we learned about the chirality of the molecule. Okay. We first understood that it can be carbon, nitrogen, phosphorus, and sulfur. It can be any atom. It should have 4 different substituents, but the flipping or whatever inversion should be around 10 to 15 kilocalories to be separable. Otherwise, they are not separable. Okay, so we try to understand that. Then we came, so we are clear with that. So we won't forget anything. So just looking into 4 nitrogen atom, looking into 4 different substituents, we won't jump immediately and say this molecule is chiral. No, we will look into whether they are separable. For that, we said that at least hydrogen atoms and deuterium core replace isotope Ranaya. If there is a 3 substituents, at least 2 of the hydrogen should be replaced. Hydrogens or the isotope should be replaced by the other substituents or other groups. That's what we understood from the chirality. Then we came to the enantiomers, and enantiomers we said what are the mistakes we will do. We said we will not look into the mirror image. We should not overlap the diagram without knowing R and S. We said that we should look into the plane of symmetry and the center of symmetry of the molecule before we conclude that it is an enantiomer. After that, we said that R and S configuration is not like dextro or levo. R and S of a given molecule will have different optical activity, that is turning of light. It's not necessary that R should turn clockwise and S should turn anti-clockwise. It is not necessary. That we remove that misnomer from our mind. Then we took the Fisher projection, and in Fisher projection we said that if it is vertical, you go with it. If it is horizontal, please change the R to S or S to R. Then we have seen how to convert wedge and dash to the Fisher projection. If the lowest, anything which is in the dash will be having the same side, we won't change the side. Okay, this is what we understood. So we understood chirality, enantiomer, and their nomenclature. So next class we'll be talking about diastereomers, allenes, and biphenyls. Any doubt or anything you think, sir? If you do like this, it will be more interesting. Or the class is interesting, keep like that. Any suggestion? Don't give me at the end of the class. There is no meaning. If you give me now itself, I can improve.
So it would be better if you keep the handwritten the things that you are writing, if that can be preserved in any way.
Preserved. Okay, fine. Okay, that's a good idea. Fine. Then, see,
Yes,
I don't want you to waste your 2 hours sitting in my class without learning anything. That is my main idea. You should feel that when you leave my class, yes, I learned things. This is okay.
Yes, sir.
Yes, sir.
Yes, sir.
You're not wasting any time, right?
Problem sheets would be, if it would
Yeah.
be given in time, that would be better, sir.
Yeah, problem sheets will be given once you finish the stereochemistry. All problems will be given together. But tomorrow you have problem clearing section. Your TA is going to clear all the problems. So she will give problems.
Sir, what tomorrow's? Yes, sir. So what about tomorrow's tutorial class, sir?
Tomorrow tutorial class you will be having a TA. They are PhD scholars, and they will be giving you problems and solving the problems.
Okay, sir.
You tell them that Sarah's teach up to enantiomer. Madam or sir, just try to teach chirality and enantiomer problems. Okay?
Sir, we haven't been mailed by any TA, so we will receive the mail by today, right?
Oh, TA has not mailed you. Okay.
No, sir,
I will then call. I will call the TA and ask them.
Our TA has mailed us.
Oh, your TA. Okay, then I will ensure that the TS mail them. Okay, because they will send a Google Meet link, I think. Right?
Yeah. Yes, sir.
Yeah, they will send that. Okay. Okay, then
So
guys.
there will be
So
lab also
there will be first year
for
lab also.
organic
No?
part.
Yeah, lab. Which lab? You have lab also. The lab will be there as regular as is. Okay. But I am taking for section 1 and 4, I think, lab class. Thursday I am taking. Thursday morning and Thursday afternoon I am taking lab classes.
Sir, you are only taking for section 1.
I think Thursday morning क्या है lab class किसका है?
Section 1.
Yeah, then I am taking. Lab class I am taking for section 1 and section 4 on Thursday. Both I am taking. So, so it was interesting. I was also interested, man. Your class was good. Nice interaction with you guys. So we'll keep like this, okay? And we'll try to learn many good things. Okay, guys.
Thank you, sir.
Okay, then. Thank you. Thanks a lot to everyone. Okay. Bye, guys.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Bye. Yeah. Bye then.
Sir.
Thank you, sir.
Yeah.
Thank you, sir. Bye.
Yeah. Bye.
Thank you, sir.